Wi-Fi electrostatic potential. An electron accelerates from rest to some place. The potential at the initial position is Vi. Potential at the final position is Vf. We know that the charge Q of an electron is a minus E, that is a negative. If it is a positive, it accelerates. We know force is a minus gradient. Force is a minus gradient of potential energy. And potential energy is a charge multiplied by potential. So the potential energy depends on the sign of a charge. Potential is fixed. So for a negatively charged particle, it acquires kinetic energy when it moves along the direction to increase the potential. For a positively charged particle, its motion, its force is from the place where the potential is higher to lower. That's difference. So anti-parallel to the electric field, F equals QE, and Q is negative. Force is opposite to the electric field. The kinetic has increased. The work done by the electric field is positive. This is because the work kinetic energy theorem. And V final is always greater than the initial because it is a negatively charged particle. And work kinetic energy theorem states that from the initial state, that is vanishing velocity, so the amount of energy acquired by the electron is EV. Here, this E is a positive, and that amount is identical to the change in the kinetic energy. From this formula, the final speed can be determined in this way. This is an application of shell theorem. We consider a non-conducting sphere of radius r centered at the origin, so uniform charge distribution, so we can apply shell theorem. The spherical is symmetric. Okay. If you look at this one, r, the radius r, this is a distance from the origin to the field point. Field point. If r, small r, is greater than radius, we don't have to worry about the detailed distribution. Instead, according to shell theorem, we replace this situation with a point charge that contains all of the charge at the origin. Here, this charge Q is distributed over a spherical symmetric charge distribution. So Q is in here when the radius is greater than capital R. Instead, when radius, this field point is inside the charge distribution, it does care about the charge contained inside this radius. And we forget about this charge. This is the result of shell theorem. So we call this QR to be the charge contained inside the small sphere of radius small r. And this is actually that amount. For example, when we substitute small r equals capital R, then what happens? This one vanishes, and this is 1 over capital R. And at the boundary point, R equals R, still this one is valid. So this value at small r equals capital R is identical to this. So this potential is always continuous function. From the potential, we can read the electric field by taking the minus gradient. Because potential is a function of R only, it depends on the situation, but we have a spherical symmetry charge distribution. So we don't have to worry about the details about any other components except for the radial component. And these are functions of small r only. And we have a differentiation table. And following these rules, we can find the minus gradient of potential to find the electric field. And the result is this and this for inner radius and outer radius. Here we find this electric field is identical to the case that contains a charge Q at the origin, point blank. However, inside the sphere, this structure is different. For example, when we substitute R equals 0, this electric field vanishes absolutely. And it is linearly increasing as we increase the radius of field point, radius of field point. The reason is that we have 1 over r squared in the distance scale. However, the charge contained inside this small shell is proportional to radius cube, because this is a volume is something like that. As a result, this divergent behavior disappears, and we have a linear structure inside the surface. Okay? Next, we consider a charge distribution. We have a dipole plus Q minus Q in here, and we have another charge Q. This one used to be at rest, and we want to move this one to the origin. We want to find the work required to move this charge small q to the origin. So this can be done by considering the fact there is no change in the kinetic energy. If there is no change in the kinetic energy, then the energy conservation states that what we have to do is to find the change in the potential energy. That's it. The initial potential energy of this system can be found by using 1 over 4 pi epsilon 0, 1 over 4 pi epsilon 0, and the product of charge and distance. Okay? So we have this distance, this is square root a squared plus b squared, and I told you c equals a squared b squared square root. This is a squared plus b squared, and this distance is 2a. So substituting these and product of these charges, we find the initial potential energy. And the final potential energy can be computed. New charge distribution is like that, and this distance is 2a, and this is a, and this is a. And using the same product of charges, because there is no change in the charge of each particle, so we have changed the denominators. The change in the potential energy is the work Wait a second. Work required to move from here is the incremental potential. This equals 0 should be deleted. Okay. Equals 0 should be deleted. Okay. The electrostatic force is conservative force, so whatever path you follow, this W is always the same. Next, we consider conducting shell. Shell is a sphere and empty inside. Of radius r centered at the origin is uniformly charged with capital Q. Inside shell is empty. Okay. The charge distribution is a spherical symmetry about the origin. One can apply the shell theorem. That's right. The potential outside the shell is identical, sure, just like the previous case. Potential inside the shell, there is empty. Haha. Potential should be a continuous function, and inside the shell, there is no electric field, so potential should be constant. Minus the gradient potential equals 0 means potential is constant. Constant means if I know this value and substitute the boundary value, that is 1 over capital R, and copy this result in here. Okay, this is a way to find this result. Okay, I take the minus gradient to this potential to find the electric field. And you know how to compute 1 over R's minus gradient. I explained in the previous problem. So it is identical to the point charge at the origin for R is capital greater than capital R, and inside the shell, electric field vanishes. So that's right. We have a circular wire of radius R centered at the origin, placed on the XY plane, uniformly charged with Q. We compute the electrostatic potential at a field point Z. This one is a Z on the Z-axis. Okay, there is a circle on the XY plane, X, Y, and this distance is G. P is placed in here. We know every point has the distance. This is R, this is Z. This distance is R squared plus G squared. Every charge on this circle has the same distance. So the integration is trivial. We don't have to integrate. It is just 1 over 4 pi epsilon Q over distance. This is the potential energy. Potential. If we know the electrostatic potential, then by taking minus the gradient, we can obtain the electric field. Because this is a function of Z only, the gradient is just third component only. And what we have to do is to take the partial derivative with respect to Z only. And the derivative is straightforwardly obtained like that. We find at Z equals 0, for example, this point becomes at the origin, then at the origin, all of the electric field due to every part is a symmetry. So there is exact cancellation. Z equals 0, there is no electric field. When Z is very large, then in z is very large in comparison with the radius. This z is much greater than the radius. Then it looks like a single point charge. Let's see. This one becomes z over z cubed. When z is much greater than r, then we can replace this with z cubed. It is just 1 over z squared. Aha, this is identical to the case of point charge. Next, just follow this calculation to find that you have to memorize this integral table. It is very important to memorize this to evaluate the following computation. We have a charge distribution along a straight wire, and at the end point, one end point is at the origin, and the length is L. Length is L, and uniformly charged. So this is the density of linear charge density. And we choose a field point in here, P, with the distance D. Then the charge element can be computed as dq equals density multiplied by the thickness. And then this one has the distance r, that is square root of d squared plus x squared. This is the charge dq, coefficient 4 pi epsilon 0, and the distance, this. And we have to, it's better to rescale this one as this one. Then you find this integral. This differential, as we already have seen in the previous problem, it is just sine hyperbolic inverse function, and that is identical to log t plus square root 1 plus t squared. So what we have to do is just to substitute this value into the integral table, and we have this result. In case this is the result for the case the charge distribution is from the origin to L. What happens to the case when the distribution is over minus L to plus L? And then we can take the limit as L goes to infinity. Then it becomes a infinitely long straight wire. For a finite wire, the potential due to this finite length of 2L charge with the charge distribution lambda is obtained like that. As you can see, this D can be replaced with the planar radius rho from the z-axis if we assume the straight line is on the z-axis. Then this is identical to this, except that we have replaced the perpendicular distance from the wire D with rho. Now, rho is the only coordinate that contribute to the potential, so we can make use of the cylindrical coordinate system. The electric field should be minus the gradient, and because the planar radius is the only coordinate that contribute to the potential, so we make a derivative with respect to rho of this potential to find the electric field. And detailed calculation that high school student can do is done completely in this expansion. Finally, what we obtain is this. Here, in the limit, as L goes to infinity, this one is just approaches 1. It's nothing. So this is the electric field. previously, what we have obtained in here, as L goes to infinity, what we find, it approaches 2L. The numerator approaches 2L, but denominator approaches 0. They are very similar. Therefore, potential itself diverges as L goes to infinity. It is strange, however, the potential is not a physical one. Physical one is the electric field. That infinite is not a physical infinite, and it is an arbitrary number that can be added to a potential. As soon as we take the gradient, that infinite is actually a constant that disappears to find the electric field finite, even in the limit L goes to infinity. That's very subtle in mathematics, but in physics it is evident. And we can find the electric field that does not carry any components except that the planar radial direction, because the potential depends only on the planar radius, rho. Therefore, there is no contribution along the azimuthal direction. There is a charge distribution of a straight wire. The electric field diverges on a single plane. On each single plane, it is divergent like that. However, this rotating component does not exist in the case of electrostatic case. So in the limit L goes to infinity, we have found the electric field due to an infinitely long charged wire. Here we have 2 factor of 2 instead of a 4. For a point charge, it is 4 pi epsilon 0 r squared cubed. In here, and it is proportional to radius unit radial vector, and this is a unit planar radial vector on the 2-dimensional plane. 4 pi, 2 pi, and it is r squared in 3 dimensions. It becomes just a 2-dimensional problem, and its strength does not follow the inverse scale because we have an infinite dimension. The 1 dimension has been disappeared. So on a 2-dimensional plane, the inverse scale law in 3 dimensions is replaced with just the inverse law. Next, we consider charge distribution over a disk with the uniform charge density, and we divide into an annular region and integrate over R. And this is a charge, and on this circle, the distance is fixed as what we have done in previous calculation. And then we have a very simple integral table that has been derived in here. Using that integral table, what we have found for the potential energy of a uniformly charged disk of radius r is like that. Again, as r goes to infinity, this potential diverges to infinity. However, what we are interested in is not a potential, instead, the electric field. If I take the minus gradient, we know only the z component appears. If I take the derivative with respect to z, this strange factor becomes like that. However, as r goes to infinity, this strange term disappears as r goes to infinity, and the only contribution is this one. Derivative of absolute of z is just the sine of z. As a result, electric field around the disk on the right and left, they are opposite direction. It depends on the signature of the axis. Sure, if it is a sigma is a positive in this way, if sigma is negative, it should be converging to the plane where the disk is placed. Now the remaining problems are extension of these basic ideas, and I'd like to ask you to review all of these problems as is written in the documents. It looks complicated, however, it is just straightforward to find those values by making use of these three results you have obtained and add them up by applying the superposition principle of electrostatics.